Good long weekend.
Yes.
Good. What questions do we have?
I feel like I had a question. I'm just struggling to remember this. On the proof 17 that you assigned last time, were we supposed to use, I guess, kind of never mind. I was going to ask if we were supposed to use the next section because that would make it much easier. The factorization.
For
the proof 7.
And then number 17 on page 16. I don't think you have to.
No, I found a way around it. I just thought it'd be even easier if you used the factorization.
You can do it with factorization, sure. Yeah, I mean, you can make the argument with using factorization. I'm not sure it's necessarily easier, but you can absolutely do it with factorization.
I'm going into it knowing this one's probably wrong. Which is not where I want to be. I'm going to be so really Masana.
Where don't you want to be? Wrong?
No, different than Masana's answer.
Oh. Different. Sometimes different's okay.
It could be the same thing.
There's more than one way to prove things, typically.
Yeah.
It's hard to find one though.
That's also true.
Weird how that works.
Sometimes it is hard to find one. But sometimes there are multiple ways.
But you also don't know which options there are. So it's worse than ethics.
Part of my PhD thesis was reproving a theorem with in a different way.
That's scary.
Well, I mean, theses in pure math are proving new theorems. That's what you do. It sounds scary. It's not.
Do that.
It is kind of scary, but it's not as bad as it sounds.
Scary.
I'm not gonna lie. It is kind of scary, but it's not as bad as it sounds. I mean,
If you think it's kind of scary, I think I'm staying away.
usually there's a barrier. They have barriers that they refer to as comprehensive exams to be able to go on to be able to do your research, kind of like proving yourself kind of thing. That's much scarier. Yeah, that's fine. It depends on what you're going for. You don't go to grad school and go to get a PhD for fun.
Yeah.
That's true.
That's not why you go.
That's not why you.
I don't think that's why anybody goes. Going in grad, it's difficult. I'm not. I mean, just from that perspective, it's a different. Going to grad school is a means to an end. There has to be a reason why you're going to go to grad school. Otherwise, there's no reason to go. In my opinion, it's just got to be whether or not it's worth it to you to go. And for some people, that's yes, it is worth it to go. And for some people, it's a no, and that's okay too. It's not a judgment by any stretch of the imagination. It's just don't. It's a bad idea to go to grad school just to put something off. You need to go in with a purpose because there are definitely days that grad school sucks.
I know someone who did that. He now has a physics PhD.
Really?
And he did it to put off getting a job, which is the funniest thing.
That's bizarre. What to do now?
Data scientist.
Yeah.
For,
Yeah, I
insurance.
agree.
Dr. Olson's husband does data science and also has a PhD in physics, which is good. Yeah.
Specifically astrophysics.
Mhm.
Is that him too? I thought I
think so. I mean, I think that's right.
Such a bizarre coincidence.
Well, I mean, it's a coincidence from the fact that they have PhDs, but it's not necessarily a coincidence you go to data science from astrophysics because that's all you have is data. I mean, you're gonna. I mean, you don't have any direct observation of
Yeah,
anything.
this is not
Oh, cool.
I learned my lesson.
Learned your lesson for what?
Not bringing your sweatshirt.
Oh, now are you cold?
A little bit.
You want to pull over? I have one in my office.
That's alright.
You sure? Okay.
Yeah.
Alright.
It's better than my last class. So.
I'll talk enough, it'll heat up the room.
Yeah. It's such a small space.
Yeah, yeah.
We'll just be yapping and
Yeah.
it'll get warm.
It is.
Yeah.
Other questions at all? I probably should do something that resembles math at some point.
Yeah. Unfortunately.
As opposed to having triggering events back to grad school for me, at least. Let's change the subject. Let's not talk about it anymore. No, it was fun. I'm not gonna sugarcoat it. Graduate school sucks. It just sucks less the longer you're in it because you get to where you're trying to go. The beginning, I found the beginning here would be really hard, but it's fine. I'm not trying to be scary. I just anybody who tries to tell you that it's all roses is lying. But
Or selling you something.
was it?
So we're selling you something.
Or selling you something? That could be. No, it's it depends on where you're trying to get to. If you're trying to get a master's to get out and get a job, I don't think that's nearly as bad as going on the PhD part, personally. That's just, but like I said, it depends on what your goals are. If your goal is, I need this degree to do this, and I really want to do this, then it's worth it. Your friend is weird to go off and just postpone getting a job.
Yeah.
That-
Spend money to
yeah.
go to grad school.
It
Well,
turned out all right.
In the sciences, you don't spend the money; they pay you to go to grad school. Typically, usually you get a tuition waiver and you teach essentially. So usually it's not. Yeah, paying to go to grad school is not something I'm not familiar with. Sorry, Jenna. That's not true. I don't think it. Yeah, you'll pay. Yeah, but ordinarily, if you go to grad school in the sciences, you get paid to go to grad school. Not necessarily well, but you get paid. But yeah, usually, well, at least in my experience, it was you taught a class, or you led in large lecture sections. At other universities, they'll have smaller discussion sections that are led by teaching assistants, and usually you have two of those if you're doing the discussion sessions. If it's a class, you usually just have the one class, but if it's discussion sessions, you usually have two. That part was the part that I wanted to do.
Yeah, that part's worth it.
Yeah, that part was fun. I enjoyed that. I wanted to go and teach at college, so that part was the part that I wanted to do, and I just focused on that and not the other. But once you get, I mean, if you're going on for a PhD, once you get past the comprehensive exams, it really, I mean, it still sucks, but you don't have classes that you have to take. The thing you have to do is your research. But if you can get past the comprehensive exams, you can find an advisor and they'll have a problem for you to work on. You will get done unless you just completely flake out. So that part's not, I mean, like I said, it still kind of sucks, but it doesn't suck nearly as much as the beginning. So the hard part's the beginning. Kind of like anything, it's new, it's scary, it's harder at the beginning than it is at the end. But anyway, grad school. Did do a lot of fun things in grad school though too. I mean, I made good friends in grad school. I still work with a buddy on research. I've been doing that for. I graduated in '98. So how many ever years that is?
26.
26, yeah.
Wow.
So been doing that for 26 years. So he and I have done a lot of work together. We've published, I don't know, 15, 16 papers together. So
Wow.
yeah, so yeah, it's been a good working relationship. A lot of the stuff that we do, we've worked with students in the past, which is what we always want to do anyway. So, like I said, it was worth it. It was just 5 years. It was a long 5 years. It happens. All right. Anyway, any other questions about algebra? Before we go on. All right. So last time we talked about equivalence relations and just briefly talked about a specific example. So remember, just to remind for an equivalence relation, if we have a set A and we have a relation on a set A, remember again that by relation we just mean a set of ordered pairs where each coordinate or component of the ordered pair, if you will, both come from A. So we can think of R as a subset of A cross A. That's all we mean by a relation. Oops. Then we say R is an equivalence relation. If what's true? What has to be true about the relation in order for it to be an equivalence relation? Yep, reflexive, symmetric, and transitive. So if one R is reflexive, and what does reflexive mean again? Yeah, so if A is related to A for all A in little a and capital A, right? Every element has to be related to itself. The second one is reflexive, or excuse me, symmetric. What does symmetric mean again? Good. And then the last one is transitive. And transitive again means? Good. Okay. Sometimes we'll write the capital letter in between the elements rather than the little tilde. But usually we'll just use a tilde, and here in a little bit we're going to talk about a specific type of equivalence relation, and we'll use even a different symbol. Because of course we will. Why wouldn't we use different symbols for the same thing? But that's okay. All right, so again, the whole idea of equivalence relation, it should make you think of equality. That's why we use the word equivalence relation. So again, with equality, everything's equal to itself. If A is equal to B, then B is equal to A. And if A is equal to B and B equals to C, then A equals C. It's kind of the mindset that you want to think when you think about equivalence relations. So let's see if we can do some verifying the things being an equivalence relation. So as an example here, let's look at number 5 on page 534. We're going to let A, the set A that we've been talking about, be the plane, so R2, the coordinate plane. And we're going to define A comma B being related to C comma D if A equals C. The problem asks you to prove that this really is an equivalence relation. So again, if we want to prove something is an equivalence relation, we need to show, we basically have 3 proofs to do. If you're asked to prove something is an equivalence relation, there's 3 proofs. Right? I have to prove it's reflexive, prove it's symmetric, prove it's transitive. I personally think that the reflexive proof has a different flavor than the other 2. The other 2 are if-then statements, right? If A is related to B, then B is related to A. So you get to assume A is related to B to start with and then prove the other way around, right? Same thing for transitive. But for reflexive, I have to show that A is related to A for everything in the set. So I don't get an assumption statement to start with, right? The only thing I get to start with is something in the set and show that it has to be related to itself. So for reflexive, we start with some element in the set that we're talking about. So in this case, the set we're talking about is the coordinate plane, R2. Things in R2 look like ordered pairs. All right, so I start with an ordered pair. What do we need to show in order to be able to say that A comma B is related to itself? What do we have to show? If it's supposed to be related to itself, if I need AB is related to AB, then what has to be true? So the relation says that two ordered pairs are related if their first components are, right? So how do I know that A is related to it? AB is related to itself. Yeah, because A is equal to itself.
Yeah.
Good. Yep, that's right. So in this case, then AB is related to itself since the first components are equal again. The A equals A. That's the entire proof to show that it's reflexive. So we really do get that it's related to itself. Now for the other ones, we get to assume something. So let's suppose that AB is related to CD. Then we just need to show that we can reverse the relation, right? Agreed? Okay. So in this case, if AB is related to CD, what does that tell us? A equals C, or basically we want to flip things around. So if A is equal to C, we also know that C is equal to A. Good. Hence, what has to be true? Good. So again, for symmetric, we're just trying to show that we flip it. We just go through, figure out how the relation is defined. The definition of this relation is first components are equal. Since I'm actually talking about equal, I know I can flip equality around, so that flips my relation around. What do we get to suppose if we're going to show that something is transitive? Yeah, third order pair. So we get to say that AB is related to CD and CD is related to EF, sure. As long as they're different letters. Doesn't really matter what we call them. You can use Greek letters if you want. You can use emojis if you want. I don't care. What's that?
Frowny face, crying face.
Right. Those selfies is what you're doing your algebra homework?
Well, this is the emoji.
Yeah.
I guess I could just put in pictures of my own face.
That'd be about the most hilarious homework as ever I got. So we went through and just put pictures of themselves doing different things for the different symbols throughout the program.
I put it on the bucket list.
That'd be hilarious. That sounds like extra credit, actually. Did you just say that?
That sounds like
It does. All right, so if we suppose that those two things are true, what's the first relation tell you? Good. And the second one tells you? Good. And then from those two statements, good. And if A is equal to E, what do you get? Good. So since the relation is reflexive, symmetric, transitive, we can say R is an equivalence relation. On R2. Not R question mark 2. Looked like a question mark. Notice that I think in this particular proof, it was a little bit nicer to use the tilde notation for relation rather than trying to say, we know relations are sets of ordered pairs, but in this case, if you wanted to write it using your ordered pair notation, it would be an ordered pair of ordered pairs, like that, right? Which is kind of ugly. So that was why we prefer to use the tilde notation or a different notation for related to rather than that, even though that's the definition. All right. So a concept, was there any questions about the proof at all? We okay with that? All right. So a concept that goes along with equivalence relations are what we refer to as equivalence classes. Now those are a little bit different than you're used to for equality, but you still have dealt with equivalence classes before. So for example, when we write things like 1/2 equals 2/4 equals whatever, 4/8 and so on, you've got different representations that mean the same rational number, right? So you're actually kind of used to doing equivalence classes, even though you don't call them that when you first use, when you first start talking about fractions. We know that they're equivalent fractions because they can be reduced to the other ones, right? When we talk about reducing, what we're really looking for is what we call a representative of the equivalence class. So when we write the notation we use for equivalence class, in this case, a lot of times we'll use brackets around it, and I'll write the definition here in a second. When I write this for rationals, this would be the set of every rational number that is equal to 1/2. There are multiple representations that we can use for 1/2. We usually use the one that's in lowest terms as kind of what we call the representative of that equivalence class. Does that make sense? Okay. So you've already talked about that. So when we talk about equivalence classes for a definition, we're going to let R be an equivalence relation again on a set A, and let little a be in capital A. Then the equivalence class of A, or sometimes you'll say the equivalence class generated by A, but not really generating anything. The equivalence class of A is, the notation we'll use typically is brackets, although on a little bit when we start talking about modular arithmetic, I might use a bar over the top of it just because it's faster to write than having to write brackets all the time. This is the set of everything in A that's equivalent. Everything in capital A that's equivalent to little a. This is what we mean by an equivalence class. Okay. So everything in the set that's equivalent to a given element. So let's go back to the previous example. The previous example said that we're defining two ordered pairs in the plane to be equivalent if their first coordinates are equal. The second part of the problem for part number 5 is describe the equivalence classes. So rather than trying to write them out in symbols, let's think about what they would be geometrically. If I start with a point, let's just think about it with a picture. Let's say I start with the point 1, 2. If I want to take the equivalence class of the point 1, 2, what is the set of every other ordered pair equivalent to 1, 2 geometrically? Well, what has to be true to be equivalent to 1, 2? Yeah, the x value is always 1, right? So what kind of a shape do you get geometrically? What kind of line? It's going to be vertical because the x-coordinates is the same, right? So this would be what your equivalence class would be for 1, 2, right? So the equivalent, if we think about it geometrically, the equivalence class of 1, 2, or in fact 1 comma anything is the line x equal to 1, right? Geometrically, that's how we would think of it. So in particular, if you had the equivalence class of a comma b, this would just be the line x equal to a. Could you make up an equivalence relation where the equivalence classes are horizontal lines rather than vertical lines? Could you make an equivalence relation where the equivalence classes are horizontal lines rather than vertical lines? What would you do instead of what we had before?
Second coordinate is equal.
Good. Yeah, just define the 2 points, the 2 ordered pairs to be the equivalent if their second components are equal. Could you define an equivalence relation where your equivalence classes are lines of slope 1? What would you need to do?
Equivalence if A over B is equivalent to, or is equal to 1, right? A over B is equal to C over B.
So
I feel like I started a thought.
it's okay.
Yeah.
Hey, spitting things out is what you do. I think I've probably mentioned this in another class before, but the way that you get presented math is so disingenuous how you get presented in class. Because usually we have this nice logical progression from point A to point B, and this implies this implies this implies this, and that's how we get there. It's not how anybody actually does math. Ever. If you're creating mathematics, you never do math in that way. You've got scrap paper over here. You've got something wadded up that's been thrown in the corner. You missed the garbage can. That's how math goes, right? You got math on boards all around the place. I mean, it's very, very disingenuous. So anytime you want to just spit things out, right or wrong, spit things out. Perfectly fine. That's how math is done. We'll talk about whether or not it's right or wrong. Okay? So don't be afraid to say things. All right. So let's say we wanted slopes of 1 for your lines. So if this is my AB, and I want to start trying to generate some other point CD. So think of this as being my starting off point. I want to make this to be a line of slope 1. What would need to be true? Well, how would you find the slope of that line? Let's start there. Ooh, that one's not a trick question. How would I find the slope of that line? Well, it would be B over A if I were going through the origin, not necessarily going through the origin. Say that again. Yeah, so the slope would be D minus B over C minus A, right? That would definitely be the slope, right? But again, that would be the slope of any line that's parallel to it. So I'm going to make sure I'm on the same line as AB. What would be the equation of that line now? Well, okay, let's start it this way. I want the slope to be 1, so I need this to equal 1, right? If it's going to be on that particular line. It's probably more work algebraically than I want to do, but we're in algebra class, that's okay. what would be the slope? What would be the equation of the line now that you would need? Ignore CD. If I wanted a line with slope 1 that goes through AB, what would the equation of the line be? Say it again. Well, if the B equaled A, again, I would be going through the origin. I don't necessarily know I'm going through the origin. So if the slope is 1, and you pass through the point AB, I gave you the slope and I gave you the point. What form of the line might be helpful to find the equation? Point slope form, right? Remember that?
Or you could just, I think you could do slope intercepts.
You could also, yeah, you could solve for that. Yeah, you can do it that way too.
Set M as your slope, then your intercept would just be B minus A if the slope's always 1.
Yep, you're right. Oops. Plus B minus A. Yeah, exactly. Yep. So this would be the line that you're trying to get to, right? Agreed? Okay. So if I want a relation to make sure that we're on a line of slope 1, I need to make sure that if I'm given the AB and I want the CD to be related to it, what has to be true? AB is related to CD if what has to be true? So that would I'd have to give you the same line. So if I want to make sure they both generate the same line, what would have to be true? So if this is the line with slope 1 that goes through AB, what has to be true if I want to make sure that CD is on this exact same line? How do you check if a point's on a line? Well, if I have coordinates, how can I? That's the idea. You plug in an x out of y that gives you another point on the line, right? If I say here's a point, how do I know that it's on the line or if it's on any graph? What do I do?
I know this is an easy question.
I know, it is an easy question. So let me ask you a different question. What's that the equation of? Oops, let's do it this way. It's a circle, cool. Is the 2.21 on this circle? How do you know? Just plug it in and check it, right? Okay. If I want to know if something is, here's the line that has slope 1 that goes through the point AB. If I want to know if the point CD is on that line, what would I do? Plug it in and check it, right? I would plug in the D for Y, the C for X, and see if I get a true statement, right? Rearrange that a little bit, you would have A minus, oops, do it this way. Well, I could do it the other way. D minus C equals B minus A, right? If I put in D for Y and C for X and then move the C over. Ooh, that was a long time getting there. That's okay. Like I said, this is how you do math. It takes a while. There was a reason why I did this, as opposed to being, mean and making you think, hurt your brains for a while. There's a reason why I did this. The original question said, I have an equivalence relation. What are the equivalence classes, right? But we could also go the other way. If I have an equivalence class, and I have something that's made up of classes, I can create an equivalence relation from it. It goes both ways. Okay. There's a special property of equivalence classes that we'll mention here in a little bit, but it works both ways. Given a relation, I can find given an equivalence relation, I can find the equivalence classes. But if I say, here are my equivalence classes, that defines an equivalence relation. It works both directions. It's an important property of equivalence relations in their classes. All right, so along those lines, there's a theorem that has several parts to it. I'm not sure it's listed in here necessarily. Oh, what part of it is? Well, the first part of this is going to be that as soon as I start talking about equivalence classes, let's assume they have an equivalence relation. The first one says that if I have an equivalence class generated by A, the element A actually has to be in there. Okay. So remember, if we go back up to our definition of equivalence class, that's our definition of equivalence class, right? What property of equivalence relations tells me that A has to be in the equivalence class generated by A? Reflexive, right? This is just a restatement of the reflexive property. So I'm just going to put that down here below it. Equivalence relations are reflexive. Good. The second property that I'm interested in is when I have two equivalence classes, there's only two possibilities that can happen of those two equivalence classes. So if I have an equivalence relation and I pick out two equivalence classes, there's only two possibilities that can happen. Either those two equivalence classes are exactly the same, or those two equivalence classes are disjoint from each other. They're either exactly the same or they're completely disjoint. Okay? So this is another one of those theorems that we can have proof by cases. Let's assume that one thing is not the case, and so then we have to have the other. Let's suppose, if you will, that they're not disjoint. If they are disjoint, there's nothing to prove. It satisfies one of those conditions, right? If they're not disjoint, then there's something in the intersection. Right? All right. So what we're going to use this element that's in the intersection as basically a bridge. Okay. What we're going to do, going through this element C, I'm going to be able to show that anything in here is also in here and vice versa. And that'll show that these two things are equal. That's typically how we prove things are equal, or sets are equal. Start with something in here, show it's in here, and then vice versa. Start with something in here and show it's in here. So they're subsets of each other and they'll be equal to each other. All right, so we're going to use this element C as a bridge to do that. Okay? But before we do that, let's remind ourselves for intersection, we know that this means what? If C is in the intersection, it means it's in both of them, right? Agreed? Okay. So this means that C is in A and C is in the equivalence class of A and C is in the equivalence class of B. How do you get in the equivalence class? How do you get in the equivalence class of A?
C is related to A.
Good. So C is related to A. How do you get in the equivalence class of B? Okay. So the fact that it's in both equivalence classes tells me that it's related to A and it's related to B. Where can you get to from there? It is related to B, right? you're actually using 2 steps to do that, right? First step I would need to do is flip my C is related to A is related to C. What property allows me to flip it around? Symmetric? Good. I can flip it by symmetry, get A is related to C, and C is related to B, and so they get to A is related to B requires transitive, right? So actually you do need both of those, right? By symmetry and transitivity, we have A is related to B. By the way, it's important that we have both, right? The way transitivity stated, I needed to be able to flip one of them. Yeah. Okay. All right. I needed both. Okay. So notice that here's where that these two so far. I haven't finished this proof yet, but so far we saw that reflexive property pops up to say that we know that in particular the element A has to be in the equivalence class generated by A. So equivalence classes are non-empty. Now we're going to show that they're either disjoint or they're exactly the same. That's where we're headed to. But we needed symmetric and transitive to be able to do the second part here. All right, but now A is related to B. This gets us to where we want to go. We made that bridge, okay? So now we're going to let, I'll call it X, be in the equivalence class generated by A. This tells me that X is related to A. But what else do we know about A? It's related to B. A is related to B, therefore, what's X related to? B. By transitivity again. And if X is related to B, then where does X live? Yeah, the equivalence class of B. Good. So anything in the equivalence class generated by A is in the equivalence class generated by B. You think you could modify the proof to go the other way? Yeah, I mean, it's the exact same proof, just literally interchange the letters A and B, and you get exactly the same place. Right? So we'll just write down similarly. All right, B is a subset of A, and hence A is equal to B. Oops. The equivalence class generated by A is equal to the equivalence class generated by B. This is an important property of equivalence classes that's referred to as partitioning up your set. So what this says is that this theorem says that equivalence classes partition a set. Partition is one of those words that has different meanings in different contexts of math. When we say partitions up a set, we mean the following. I'm going to write it as a finite partition, but you can have infinite partitions of sets. I'll write it as a finite partition. So if I have S is equal to A1 union A2 union to AN. I'm only going to write it as it can be infinite. I also don't, as we haven't talked about countably infinite here. It also doesn't mean that I can list them out. I mean, unlike for real numbers, you can't list the real numbers. That's what uncountable means. I can't write them as a list, no matter how hard I try. You can also have an uncountable partition of a set. Okay, I'm going to write it as finite this way. So when we say we have a partition, I mean my set is a union of sets where each set is not empty, and they're pairwise disjoint. I guess I could have written it infinite, but I was going to think about it as finite because most of the stuff we're going to do is finite. Just know that when I wrote it as a finite, you can extend it to an infinite union. You can extend it to an uncountably infinite union, if you would like. The important parts of being a partition is that you've written to the set as a union of smaller subsets, where you didn't throw the empty set in there because that's stupid, and you don't have any overlap. Okay. Which is exactly what we said we had when we had equivalence classes, right? We have each equivalence class is non-empty. The representative we have for the equivalence class is in that equivalence class, right? And certainly I can make my entire set be a union of the things of equivalence classes because, again, I can take every element in the set has to be in the equivalence class generated by that element, right? So it certainly is a union. And if I look at distinct equivalence classes, I get a partition. So equivalence class is partition, all right? Now, going the other way, like I mentioned before, equivalence relations give us equivalence classes, but we can also do equivalence classes give us equivalence relations. We can go back both ways. What that means is that if I start with any partition of a set, I can create an equivalence class out of it. Or, excuse me, I can create an equivalence relation out of it. It works both ways. So start with an equivalence relation, I get equivalence classes. Start with a partition and treat them as equivalence classes, I can generate an equivalence relation. It works in both directions. I know that was a lot of words. Okay. We're going to be concentrating on some very specific equivalence relations in the next section. But just to give you some illustrations of things that aren't equivalent, that are familiar relations that are not equivalence relations, let's think of some things. So as an example here, if we let, doesn't matter, let's just let A be R and let our relation be less than or equal to. That's a familiar relation we're used to, isn't it? This satisfies two properties of equivalence relation, but not a third. Okay, so remember, equivalence relation has three properties: reflexive, symmetric, transitive, right? This one, I said, satisfies two of them, but not the third. Does this satisfy reflexive? Yes. Everything is less than or equal to itself, right? So it's reflexive. Does this satisfy symmetry? If A is less than or equal to B, is B necessarily less than or equal to A? No. Just make them not equal and you get that it's not symmetric, right? Is it transitive? If A is less than or equal to B and B is less than or equal to C, is A less than or equal to C? Yes. So it is transitive. So then less than or equal to is reflexive and transitive, but not symmetric. This particular relation is something that's referred to as antisymmetric. Unfortunately, antisymmetric does not mean not symmetric. Okay. Antisymmetric is that if you know that A is less than or equal to B, and you know that B is less than or equal to A, what had to be true about A and B? They're equal to each other. That's antisymmetric. So antisymmetric says that if A is related to B and B is related to A, then A equals B. That's antisymmetric. But that's not the same as not symmetric. You can have a relation that's not symmetric and not antisymmetric at the same time. Okay. when you have a relation that's reflexive, antisymmetric, and transitive, we refer to that as a partial order. Actually, in this case, we also get a linear order, but that's a different thing. If you would have started with, no, I was going to write it down. It's the exact same. It's the exact same idea, but just for sets. Let's just let S be any set, and we'll let A be the power set of S. 4 of you should remember what power set is.
We're almost there.
Remember what power set is? Let me ask a different question from a specific example. If I gave you the set 1, 2, and asked you to create the power set of that set, what would you do?
Set of all possible subsets.
That's it. It's the set of all possible subset. Yeah, that's what the power set is. Yeah. Did you already learn that in discrete?
We talked about it last time.
Ah, cool, good. All right. Power set is a set of all possible subsets. We're going to let subset be our relation. What do you think? Reflexive? Is everything a subset of itself?
Yes.
Yes. If A is a subset of B, is B necessarily a subset of A? No, so it's not symmetric. If A is a subset of B and B is a subset of C, do you get A as a subset of C? Yes. So again, it's reflexive, not symmetric, and transitive. This one also happens to be antisymmetric. But why? And this is exactly why we use the subset symbol with the rounded off versus the pointy one. It's supposed to make you think less than or equal to. It's the extension of less than or equal to sets.
Is it fine if I like quotation marks around the symbols?
Yeah, that's fine.
These I think are confused.
Yeah, that's fine. You can put quotation marks around it. That's fine. So exactly the same conclusion as what we had before. Let's see if we can do one with a specific set and then ask you to create particular types of relations. So this is number 8 on page 535. We start with a specific set 1, 2, 3, and it asks us to create a relation on A that satisfies the following. So let's make it reflexive. The first one is reflexive, not symmetric, not transitive. So in this case, it really wants you to make the set of ordered pairs that satisfies this. Let's do the reflexive first. Reflexive again means what? A is equal to, A is related to A for every single A in the set, right? So if we're going to create a relation that's reflexive on A, then we have to have what? Yeah, we have to have 1's related to 1, 2's related to 2, 3's related to 3, right? We'll use the ordered pair notation. So we have to have 1, 1, 2, 2, 3, 3 in there, right? Agreed? Right now, though, this relation is symmetric and it is transitive. As a matter of fact, this is an example of which relation on A. The way we have it written right now. This is a very specific relation on A. What is that relation? 1's related to 1, 2 is related to 2, 3 is related to 3, and nothing else. What relation is that? Yeah, it's just equals. Exactly. Yeah, A equals A. Yeah, it's just equality, right? So this relation right now is symmetric and it is transitive. It's just the equality relation. So throw something in there that makes it not symmetric.
That's my symmetric views. 1, 2.
Okay, and put it in a 1, 2. But if you wanted to make it symmetric, what would you throw in there? 2, 1, right? Yeah. Well, we don't want it to be symmetric, so let's just leave it 1, 2. Now we've made it not symmetric, right? We also want not transitive. Unfortunately, this one is still transitive, right?
Yeah.
Yeah, because the only thing I would have is 1's related to 1, 1's related to 2, so 1's related to 2, that's okay. Or 1's related to 2, 2's related to 2, so 1's related to 2, and that's still okay, right? So to make it not transitive, what can we throw in there? 2 is related to 3, good. And that'll take care of it. Yeah. That okay? Can I modify this to do, just literally take that same relation and modify it to make it reflexive and symmetric, but not transitive? Can you take that exact same relation that we just did in part A and make it reflexive and symmetric, but not transitive?
You can start the same way.
If they get too loud, we'll just shut the door. If they get too loud, we'll just shut the door. I don't want to shut it. Go ahead and shut it. Cool, thanks. What we, if we wanted the relation R in the previous one to be symmetric, BE symmetric. Oh wait, sorry. Makes you think of be aggressive. BE aggressive. Sorry. that was what went through my head. Sorry. Would it be symmetric? BE symmetric. Sorry, that's just what went through my head when I said it. Especially the way I said it. If you wanted to be symmetric, be symmetric, exactly. What would you need to add into that relation and make it symmetric? 2 is related to 1 and 3 is related to 2, right? I would need to add both of those things in there. Does that do it?
Yes.
Yeah, that does it, right? Because it would still not be transitive. What element in particular is not in R that makes it not transitive still? 1 to 3, right? And if I do the other way around, 3 to 1 would also be in there. So we can just add to 1 and 3 to the previous relation. Okay, does that make sense? All right. Anyway, so again, this is number 8. Look at there's like 4 other parts to that. See if you can think through those for later. I do want to give you a couple of problems to turn in out of this section. They're both a prove that something is an equivalence relation. This is 13 and 16 on page 535.
Where do you want us to turn in the ones from last week?
Where?
2 questions. Yeah, like how do you want us to? Just like on paper give.
Yeah, on paper, give it to me, or if you've got it written on your iPad, you can just email me.
Okay.
That's fine. Either or, I don't care. If you know how to type it up in LaTeX, you can do that too. I'm guessing that's not something you're interested in.
Olson promised to teach me.
Was that?
Said Olson promised to teach me that.
The easiest way that I know to learn LaTeX is to take a document that somebody actually has that already compiles and work from that. It's the easiest way I know how to do it. Because it's basically computer programming. You've got stuff that you have to set up that needs to get loaded in, and then you've got to tell it if something is text or if something is math. Because if you try to do something in math that's in text, it hates it. And if you try to do text in math mode, it's just going to put it all together like it's a math symbol. So but it makes pretty documents. That's what I type my stuff in. So anyway, so the reason why we went through equivalence relations is because we want to talk about a specific type of equivalence relation, and that's what we typically refer to as a congruence relation in modulo n. So this is section 2.1. This is what they call congruence in congruence classes. And in particular, this is going to be in the integers. But when you see congruence, we mean equivalence. And when you see congruence class, we mean equivalence class. They're synonyms here. It's just that typically when we do modular arithmetic, we use the word congruent versus equivalent. Okay. All right, so to start this off, this is probably going to be a very familiar definition anyway. We're going to let A, B, and N be integers with N not equal to 0. Your book's going to make it greater than 0. Fine, I don't really care. It doesn't really matter. Again, N and negative N for our purposes are essentially the same thing when we're talking about divisibility, because again, we can divide by 1 or we can divide by -1. Those are units no matter what. So if it's congruent to n, if it's congruent modulo n, it would be congruent to the modulo the opposite of n. So you can just move the negative sign to the other side of the equation, essentially. All right. So we say that A is congruent to B modulo n. And rather than saying modulo every single time, that has 3 syllables, we typically say mod because it only has 1 syllable. A lot easier to say. So A is congruent to B mod n if n divides A minus B. Your notation for this is that so the 3 bars is congruent to. Sometimes they also say is equivalent to. That's another way we say the 3 bars. So it just looks like an equal sign on steroids. You can also actually use the congruence symbol that you used back in geometry class. That's another one that is used, but usually we just use the 3 bars rather than the little tilde over the equal sign. But that's a perfectly acceptable symbol as well for congruence. Okay. Also, a lot of times, the symbol by itself doesn't make any sense. You need to know what you're doing congruent mod with. So what I mean by that is that if you change what you're modding out by, then you change whether or not they're congruent. So for example, what I mean by that is 9 is definitely not congruent to 6 mod 2. But, oops, 9 is congruent to 6 mod 3. Nine minus, if you do just by the strict definition, 9 minus 6 is 3. 2 doesn't divide 3. But however, 3 does divide 3. So 9 is not congruent to 6 mod 2, but 9 is congruent to 6 mod 3. So it matters what you're talking about when you're, what number you're modding out by when you're talking about congruence. So it's important to write it for which one. I don't care as much if you write the parentheses around the mod n, because that helps talk about what you're talk about what you're. As long as you say it's mod whatever, the parentheses don't have to be there. Is what I'm trying to say. Sometimes you'll see this written as a little subscript on the equivalence or the congruence, and that also tells you. So you don't have to write the mod in every time. For practical purposes, I mean, we're writing it as n divides a minus b. But another way to think about it is that if I divide n by a, let's try that again. If I divide a by n and divide b by n, I have to get the exact same remainder for them in order to be congruent modulo n. Because if I want n to divide a minus b, if I do the remainder when I divide remainder for a when I divide by n, and I do the remainder for b when I divide by n, those have to cancel out when I subtract them. Okay, so they're going to have the exact same remainder, which is a little bit easier to look at here. Remainder when I divide by 2 here is 1, here it's 0. So they're not equivalent. But here the remainders are both 0, so they are equivalent. So then probably the easier way to think about modular arithmetic is in terms of remainders when you divide. The only part where it really gets tricky is when you do negatives for your a and b. Remember, your remainders have to be positive. So if you wanted to look at, say, negative 7, and I wanted to mod out by 4, I wouldn't say it's 3. Okay? What I mean by that is it's a little tempting to ignore the negative sign and divide the 7 by 4 and get a remainder 3 and think it's 3. The problem is that that negative sign matters on dividing out, right? Because your remainders all have to be positive. Okay. So really, this would be, if I think about it in terms of remainders, it'd be 1 mod 4. From the definition, you would say this is true because 4 divides 1 minus a minus 7, right? 4 divides 8. 3 doesn't work. 3 minus a minus 7 is 10. 4 doesn't divide 10. Does that make sense? So it gets a little tricky when you're with your negatives. It's not too hard to figure out as we go.
Why is it 1 minus negative 7 instead of negative 7 minus 1?
Good question. Does it matter?
I'm assuming no.
Okay, why wouldn't I do it that way? Oh, I could do it that way because 4 divides 8 and 4 divides negative 8. So the order doesn't matter. You're right. The way I wrote the definition, I should have done negative 7 minus 1. But what do you think happens now as far as the relation? Do you think it matters? No. Okay. So the theorem is congruence mod. I'm going to write it that way. Congruence modulo n is an equivalence relation on Z for all n greater than 0. And that's why it didn't matter, because it would be symmetric. So A congruent to B is the same thing as B congruent to A. So again, if we wanted to prove this, we would do the 3 steps that we need to show for equivalence relation. It's interesting because my pause button is gone for my recording. hope it's still going. The pause button's gone. It's usually over here. Don't know where it went. It's fine.
Usually the time's up there too.
Yeah, I don't know why it's not there. So this is okay. Well, I can still pause it afterwards, so it's fine. I was just trying to figure out what the heck was going on. All right. Anyway, what's that?
I hope nobody forgot any of the last 10 minutes since it disappeared.
Yeah, it's weird. All right. So for reflexive, I would need to show what is true.
When you hit its knee, its leg kicks out.
Say it again.
When you hit the knee, the leg kicks out.
Oh, it's reflexive. Reflex. Yeah, good.
They can't all be winners.
You like BE symmetric? You gotta smack on the knee and see if it kicks. Small classes where you know everybody. It's awesome. Love it. All right, so what do we have to show for symmetric again? Or symmetric. Reflexive again? Is related to itself, right? So if we let A be an integer, if I want it congruent, if I want A is congruent to A modulo N, what do I have to show by definition? What does N have to divide? Yeah, divide 0. Yeah, so A minus A. Good. Then N divides A minus A, because certainly N divides 0, right? Anything divides 0. Okay. So A is congruent to A mod N. Symmetric, what do we start with?
A and B. And reverse the order.
Good. Reverse order. Good. So we'll start with A is related to B mod N, or A is congruent to B mod N. And we need to be able to reverse the order. Let's do this a little painstakingly, make sure that we actually use all the definitions so we can see this out. By definition, if A is congruent to B, what do we know? Yep, they know the range is the same, or said another way.
N divides A minus B.
Good. N divides A minus B. Again, let's do this painstakingly. The definition of divides is what? We rewrite division in terms of multiplication, right? So there exists, I'll call it an integer x, such that nx equals A minus B. I don't need the parentheses on that side. In order to reverse the order, sorry, said order twice. In order to reverse the order, what do we need to show n divides? B minus A. So what do you need to do to both sides to see B minus A rather than A minus B? Multiply by -1? Yep. And I'll put the negative x, or put the negative with the x, I should say. Well, n times negative x equals B minus A, which gives us what? Yep, good. N divides B minus A, hence B is congruent to A mod N. And that's why it didn't matter if we did the 1 minus a minus 7 or minus 7, negative 7 minus 1. In the last minute here, let's see if we can finish off transitive. What do we start with for transitive? Okay. Yep. A is congruent to B mod N. And B is congruent to C mod N. And we want to show what? Yeah, A is congruent to C, right? I mean, you basically get rid of the B. You get from A to C, right? The first congruence tells us what? Good. Second congruence tells us good. And we want to show what? Yeah. All right. So looking at this, if I have A minus B and I have B minus C, what's the easiest thing you can do to get rid of the B? Just looking at A minus B and B minus C, what's the easiest thing you can do to get rid of the B? Add them, right? Yeah. And if I know that you divide each piece, do you divide the sum? Yeah, that's one of our theorems we've already proved, right? So N divides A minus B plus B minus C, or N divides A minus C, hence A is congruent to C mod N. Excellent. So what we've shown now is that congruence is an equivalence relation. So now we can start talking about equivalence classes modulo a number. We already said that two things are equivalent if they have the same remainder when you divide. So just as a quick example, I know I'm out of time, but if we do a quick example, if your N is 5 and you wanted the equivalence class of 0, you want everything that has the exact same remainder when you divide is when you divide 0 by 5. So what are you looking at? All multiples of 5, yeah. So you'd have like negative 15, negative 10, negative 5, 0, 5, 10, 15, and so on, right? What other equivalence classes would you have? Not only have how many other distinct equivalence classes would you have? One remainder was 0. Yeah, we'd have 4 more, right? We'd have 5 total. You'd have equivalence class of 1, 2, 3, and 4 to go along with 0. Yep. We'll play with that more next time. Have a good one.